So, dann herzlich willkommen zurück zu einem weiteren Talk von Filmröllchen. Es geht um RISC-V. RISC-V ist die Zukunft, sagt Filmröllchen. RISC-V ist eine Prozessorarchitektur, die Open Source ist. Und das ist was Faszinierendes, weil normalerweise hört das Open Source beim Source Code auf, dann kommt irgendein Compiler, der ist auch noch so Open Source und dann kommt irgendwann ein Prozessor, der ist closed und Propriety und kein Mensch weiß, ob das, was man da ausführt, tatsächlich auch ausgeführt wird. Und das ändert sich mit RISC-V und Filmröllchen erklärt euch jetzt so ein bisschen die Basics von RISC-V und wie das Teil eigentlich funktioniert. Bitteschön.
Okay, thank you. I will talk about RISC-V, which I very try to provoke everyone and try to piss everyone off by saying it's the only architecture you'll ever need, or microcontrollers, embedded systems, desktop CPUs, accelerators, servers, pick all, or as the RISC-V International puts it in corporate speak, enabling a new era of processor innovation through open collaboration. So this is going to be a basic talk, and I'm going to split it up into two parts. Oh wait, this is my introduction slide maybe. So the main thing that I have in relation to RISC-V is that I belong to the org. It's free, you can do it as well. And also I do a lot of stuff on the architecture. I really like it. And so, but I'm not professionally affiliated technically with them. Like not even RISC-V International is paying me to say anything I say here. This talk is structured into two parts. The first part is for all the people that don't know a lot about processor architectures and so on. I'm just going to tell you a basic high-level overview of what it is, why it's interesting to you, and then I'm going to have the second part, which is very non-technical and is going to be more in detail, and I'm going to look at some assembly code and so on. So if you're scared of that, you can just leave or close your eyes or whatever. I don't care. I hope there will be some Q&A later. So RISC-V, always pronounced like this, is an open standard for an instruction set architecture. So open as in freely open source, you can do whatever you want with it. The exact license, I'm not actually sure, but it's very much like BSD, so you can do anything as long as you don't use the name RISC-V for anything that's not officially associated with it. It standardizes the instruction set architecture, which is not the implementation or the microarchitecture. So the difference is that the instruction set architecture is what the programmer sees. So that's the machine code, the lowest level of code that gets run and what effects that has. And those are all visible to the programmer. And the microarchitecture or the implementation details are not visible to the programmer. This is very different actually from a bunch of other implementations which are always, or a bunch of other ISAs which are always based on one particular implementation, and they always carry around some baggage from some implementation or whatever. x86 and MIPS are great examples of that if you want to research that. But RISC-V isn't like that. And the name, of course, RISC stands for Reduced Instruction Set Computer. It was an idea in the 80s to reduce the power consumption and area necessary for chips by using very, very few instructions. You will see that RISC-V also has very few instructions in the most basic variants. And by that, you can make implementations very simple, very fast, and also students can design them and stuff. Nowadays, the difference between RISC and CISC, so the other complex instruction set computer, is kind of blurred, but it still has that heritage. And the number 5 comes from the fact that Berkeley, University of California, Berkeley, who started designing RISC-V, and that was their 5th major design that they did as a university. And before they designed Spark and various other architectures. So they kind of know what they're doing. I'm going to spend a little bit of time discussing why not other architectures and why RISC-V is maybe better than other architectures. With x86, which is the most common thing that you have in all of your laptops, I hope you're making a joke if you actually want that to continue for any longer than it needs to. It is extremely power hungry. Its application scope is relatively narrow, at least nowadays. It is insanely complex. It's also underspecified, which is a great combination. And it is, of course, not free. Intel mainly owns the IP, and some other companies can do stuff with it. But I don't think it's particularly easy or cheap to buy IP cores, so cores that you can take on your own and put them into your own hardware designs for x86. So basically, x86 needs to die as soon as possible. However, there's also ARM. You've probably heard of it. It's in all your phones. It's pretty great. Like RISC-V, it's very power efficient. It is also a RISC architecture. It is suited for a bunch of embedded microcontroller stuff and so on. This ISA is relatively simple. However, of course, it is also proprietary, and ARM can decide what it does with it and what it doesn't. And if it doesn't want to sell you a license, you're out of luck. And also, you always have to buy a license. You can't just use an open source design, which would be an argument for MIPS or OpenRISC. Most of the, all of the other open source architectures that are not dead are smaller than RISC-V. I've actually forgot to put something like PowerPC Little Endian in there because apparently that's people like that. They're either smaller or like MIPS are dead. And OpenRISC also in particular is tied to a specific implementation, and that's true for a lot of these. And RISC-V is, I think, really the only one where there's a lot of different implementations and different ideas coming from a lot of different places together to make the ISA. So let's discuss why RISC-V is cool on a little bit more of a technical level. RISC-V is very modular, and it's one of the most modular instruction sets that exists. So the base ISA just contains the bare minimum stuff that you need for a Turing-complete microprocessor. And it's basically enough to make like a very, very simple microcontroller. But you can have a variety of extensions, and many of the common extensions, also the ones that you would want in your desktop computer, they are all standardized. And also, if you as a company or as an individual want to have your own special extension that nobody else has done before, there is a very standardized and specified way of how you can do that so that you don't interfere with any other standard extensions or anyone else doing anything else with the architecture. So this is why it's so great for application-specific processors. I'm going to mention a bunch of the interesting standard and non-standard extensions later on. And in terms of implementation, so this is just cores, so just the microprocessor itself. I would say the two most important open source ones, at least in my opinion. First of all, Boom, Berkeley's out-of-order machine, is the most complex, deeply pipelined, out-of-order executing open source design by Berkeley. And the CVA6, I at least have to mention it because I worked on it for my bachelor's thesis, which is a pretty neat design for microcontrollers, which is also pipelined, but in a relatively simple in-order way, if you know what any of that means. By the Open Hardware Group, originally also by universities. Sci-Fi makes a bunch of the main cores that you can buy nowadays. They're pretty cool. Western Digital has done some stuff which is also now open source. And there's this interesting one, Serve, which I found, which is an extremely tiny FPGA one because it processes stuff in bit by bit. So it's really interesting for certain applications. Alibaba's T-Head semiconductor division is doing amazing work on really high performance cores like the C910. And there is also functionally safe cores, so they have proven safety and can be used in things like aerospace and trains and stuff. So there's many, many, many more. This is just a small selection. I probably missed some important ones. But yeah, in terms of actual hardware, not just the cores, but also full systems, it's not just all microcontrollers, despite what you might think. There is the various Hi5 boards, the unmatched RISC-V, which is one that quite a few people have, and the Pro P550, which should be coming out or is already out. And those are basically micro ATX desktop boards with all the features that you might expect from that. There is the Vision 5.2, of course, which is a Raspberry Pi equivalent single board computer. I'm going to try to lift it up and show it into the camera. You can see it's a little bit larger than the Raspberry Pi 4, but it's pretty much also performance matched. And as you might have guessed, and as many people already figured out, I'm running the presentation off of that right now in Firefox. So yeah, it works. It's just running Debian, Linux, whatever. It's pretty normal. You can touch it later if you want to. So SciPete is doing a bunch of different devices, single-board computers, laptops, small-factor desktops. Pine64 apparently is going to make an experimental convertible laptop based on RISC-V. There is also the BeagleV Ahead single-board computer, and of course the various newer ESP32 chips, like the C6, which I have a dev board for here, or the C3. Even have a different C3 dev board. Went down here. It's very tiny. So yeah, these are all, of course, microcontrollers, and there's a bunch of other microcontrollers, also very, very cheap ones. But I think that's probably the best place to start for you, because those, of course, are very inexpensive. So I just have some larger images, also for the stream, the Vision 5.2. That's what it looks like. And this is the Sci5 Hi5 Unmatched. I think it's the original one. This one is running FreeBSD because you can. And this is the ESP32C6, which, by the way, is also a dual-core system. So, yeah. That's basically the non-technical part. You should care, because anyone can write an implementation. In fact, I did write an implementation for a university course. If you just put yourself to it for like 2 weeks, you can just throw something together in Verilog, flash it onto any normal FPGA, and just write software for it that you compiled with a standard compiler like GCC or Clang. There's no costs in terms of the architecture itself. You don't have to pay any patent costs, no licensing fees for the architecture, maybe for the IP core, of course, but not for the architecture. And yeah, anyone can sell proprietary implementations or buy them if they want to. It's very extensible, configurable. So if you have some specific needs, some specific operations that your processor needs to be able to do, it's very suitable to take this as a basis and then put some small bits on top. And also, which I didn't mention before, there is a huge, robust test set from RISC-V International, or from the various people that work on this, which makes sure that all your memory models are correct, that all your basic implementation features are correct, and that your implementation behaves exactly the way it's supposed to. And this is all open source software as well. And you will actually see later, I didn't put this on there, that most of the firmware stacks are also open source. So that's also very great. So let's get into a bit more technical details. I'm going to assume that you have some basic idea of machine hardware, computer architecture, stuff like that. Also assembly programming. So we're going to get into the weird way that RISC-V names its extensions. The base ISA is called I. There's 3 different sizes, 32, 64, and 128 bits. The Vision 5 here, for example, is 64 bits, while the smaller ESP32s are all 32 bits. The 128-bit is not yet used, but it's already specified for future proofing. And that's the size of the base integer registers, basically, and also the size of the memory bus, or at least the ISA visible memory bus. There are a bunch of standard extensions, which some of them have single letters, some of them have a leading Z and then some other name. And there is a bunch of non-standard extensions which have the X. And for example, here, if you know what Cherry is, like the hardware pointer safety thing, it's very easy to just throw that on top of RISC-V as an extension. So that's cool. Of course, you can have dependencies between extensions because you sometimes need features from other extensions. So the base architecture just has 40 instructions for the 32-bit variant. It basically just has ALU operations, memory accesses, calls, branches, and system calls, actually. There's not even multiply and divide in there, because for very simple microcontrollers, that is already too much complicated hardware. There are also no control registers, there's a little bit of interrupt functionality, but only very basic. So The registers look like this. There are, like usual for RISC systems, there is a very large register set of 32 registers that are named X0 to X31, and the program counter is not a general purpose register. And the only special register here is the first register, X0. It is always constant 0, so when you read from it, you get 0, and when you write to it, the value is discarded. And you can synthesize a bunch of operations with that. We'll see a bunch of examples of that later. The other ones are just assigned certain functionality based on the standard ABI, and that just means that implementations will make certain assumptions about how certain registers are used, but technically you can use them any way you want. So for example, return address, stack pointer, then there's split between temporary variables, which are always overwritten randomly by code that you call. There's function arguments, and there's registers that the function you just called, so the callee will save for you. But again, those assignments are all arbitrary. And yeah, okay, it's kind of slow. Firefox is not particularly fast on this. As you might know with, oh no, I'm also missing a font, so this is kind of hard to read. So as you might know with RISC architectures, they're usually load store architectures. This is very different if you know something like x86. So basically there is a split between actual arithmetic and logic operations and memory operations. Arithmetic and logic operations only operate on registers, and usually you have actually two source registers, or one source register and one immediate operand, and then you have a destination register. So for example, we can see in the third line, it's add T2, T0, T1 in RISC-V assembly syntax. That means we add T1 and T2 and store it into, we add T0 and T1 and store it into T2. So it's always source destination, source 1, source 2. That's the order, right? And then the other kind of operations are the load and store operations. There's just one addressing mode, which is register plus offset, and the offset is an immediate. So like, for example, load word, I think it should be T0 offset 4 from the stack pointer, so it's loading something 4 bytes starting from the stack pointer, so basically one word after the head of the stack pointer. Forgot to mention, words in RISC-V are always 32 bits, no matter what size of register you're working on, so RV32 or RV64 or whatever, it's always 32-bit words. And so that's why load word will load 4-byte word, 32-bit value. And then there's load byte unsigned, we do the add, and then we store the word back. So you have to do all the operations in registers. Down there, that should be shift left then, and also add immediate. Or is it, no, it's SLT, it's set less than, that's basically a comparison, storing the result somewhere. So there's a bunch of things you can do there. I'm not going to show you all the operations because they will all be familiar. It's very standard stuff. So one issue that arises with the immediates that I already showed on the previous slide is that they can only be 12 bits due to how they are encoded. So what do we do if we want to load like certain 64-bit constants, for example, into a register? Well, let's start with 32-bit constants, because for that we can use things like load upper immediate and add upper immediate to program counter. The latter one is my favorite instruction, first of all because it's named hilariously, because the abbreviation is hilarious, and because it does really great things. So load upper immediate will just load a 20-bit upper immediate into a 32-bit word. That's in the first 2 lines. You can get the constant 1, 2, 3, 4, 5, 6, 7, 8, like that. And you will see a lot of these standardized sequences, which are basically macro ops, which can be fused together in the microarchitecture, which is a thing that all modern architectures do. But RISC-V really makes it easy because it has a lot of these standard sequences. Now, AUIPC, as I like to call it, I'm not sure how you actually pronounce it. It does the same thing as Louis, so the 12 bits on the 20 bits on the top of the 32-bit word. However, it will add that to the program counter. So this is a way of getting the current program counter and for calculating an offset from the program counter, or as in this case, you can see these two instructions allow us to encode any relative jumps plus or minus 4 gigabytes, plus or minus 32 bits. So this actually makes RISC-V really, really good at position-independent code because by default, all references to other functions and other jump locations are all relative. So you need much less, and I actually checked this, you actually need much less relocations, dynamic relocations at runtime because you don't have to do all the absolute fix-ups that x86 needs, for example. Okay, that's enough of telling you about how great our EPC is. Let's talk a bit about control flow. There is no flags. That's probably the most unfamiliar one because even a RISC architecture like ARM has flags. You can only perform branches on certain concrete operations like branch equal, branch greater, branch less than unsigned, and so on. And they will always jump to a certain offset from the current instruction. Jump and link, or the two different jump and link instructions are the way that we encode unconditional jumps, but also various kinds of calls and returns, so various ways of calling subroutines. Jump and link, the link part basically means that we write the next instruction's address, not the instruction itself, but the next instruction's address to the destination register. So if you do things like jump and link and then the destination address is a 0 register, you just have an unconditional jump, right? Because the destination address is discarded. If you jump and link, have the return address register, which is just x1 as the destination, and then you jump to some function, that's a call, because then the function can use the very last one on the bottom, jump and link register 0 with a 0 offset from the return address to jump back to what was stored in the return address, and of course discard the next instruction because we don't care. So that's, I think you're seeing how the 0 register allows us to create a whole bunch of functionality just from existing instructions by combining them in clever ways. And that's something that RISC instruction sets are really good at, and RISC-V is also really good at, so that's great. And you can also do tail calls and stuff. So you might wonder, I'm just gonna talk about this briefly, you might wonder how do we do like call stacks and stuff like that, because on other architectures, if you do a call, the return address immediately gets stored to the stack. Well, you have to do that manually yourself, of course. So usually most functions that call out to other functions will have at their entry point, will store the return address that they just received onto the stack, and then they will pop it off the stack at the end. However, if you don't actually call anyone else, so you're a tail function, you don't have to do that. You can just keep the return address around and return to it at the end, which is a clever optimization that, for example, x86 doesn't get to use. Okay, let's talk about floating point. I'm going to let you take in the slide for a moment. As it says on the very top there, it's just IEEE 754. I'm not going to spend too much time on it because all the floating point stuff behaves like you would expect it to. The main interesting one is, of course, there are 3 different extensions for the 3 different floating point sizes that you would want. And I mentioned before, for example, that the double floating point, of course, depends on single floating point because that just makes sense. You have 32-bit floating point registers, except they're the same as the integer registers, but the 0 register doesn't have any special function in this case. And the way that you store, if you're using both single and double floating point, the way that if you have a double floating point extension, the way you store single floating point values is you NaN pack them into double floating point values. So basically not a number, a NaN value in IEEE 754 has a payload, and that payload in the Mantissa 52 bits is large enough to store a full single floating point value. So this is actually a trick that has been used in decades by JIT compilers and like JavaScript engines and stuff like that. But now they're making use of it on the hardware level for not having any extra registers. So whenever you're calculating with 32-bit integers 32-bit floating point values, of course. You're NAND packing them into 64-bit floats. So whenever you accidentally switch back to 64-bit floats, you don't get any garbage values. You get known values that are just NANDs, which will just have expected and defined behavior. I think that's the most interesting thing. Like the rest is just, you have loads and stores. You have bit exact transfers between floating point and integer, which apparently x86 doesn't really have, at least before SSE. There's only one transcendental function, which is square root. There's no instructions for sine, cosine, or whatever. There are no exceptions because there's also, forgot to mention it earlier, there's also no divide by zero exception for integers. So there are also no exceptions or interrupts for floating point stuff, which is allowed by the specification before you ask. And so they have a special control register for that, which stores all the exceptions that have occurred. So if you actually need to know whether an exception happened, you have to check that register. You have fuse, multiply, add, which apparently compilers really like. I don't know. A lot of people complain that it takes up a lot of encoding space, but apparently compilers like it, and it makes code fast. So I guess it's great. Also, there is some interesting sign injection instructions for a bunch of these sign-related functionality. Ask me later if you want to know more about those. They're really cool. I have to continue because I have a lot of stuff to still go through. What I already alluded to is that there's not just the normal registers. There's also a large collection of special control and status registers, which are in the CICSR extension. Here's where we get into weird extension names. So actually, there's not 4,000 defined at the moment. There's like 200 defined, and that only if you actually use all of the various hypervisor extensions. So you probably have much less than those. They have many, many different purposes. There's like the floating point ones. There's other ones that you can access from user mode, like counters and timers that will, for example, tell you how many instructions have been executed, allow you to do performance monitoring that way. Most of them, however, are, of course, for system-level configuration. You can configure traps, exceptions. You can do the address translation stuff through that. There's various hardware information in there, and much more. Like you have to look at the specific extensions and see how they use the CSRs. So since we're already speaking about system-level stuff, let's get into system-level stuff. RISC-V has 3 privilege modes. But you don't even have to implement all of them. So by default, you just have M mode, which is machine mode. And by the way, the name mode is the same as exception level in ARM and ring in x86, if you know about those. Machine mode, of course, can do everything. It's intended for really simple systems like these microcontrollers. They technically have only M mode, except in this case, you don't really need to care about it. It's also used by firmware in more complex systems. S mode is only present on like these chips which run normal user operating systems. S mode is supervisor mode, so it's intended for kernels and hypervisors. It can do things like interrupt handling and memory management. And user mode, of course, can do nothing. I mean, it can execute normal application code, but it's the highest, lowest privilege level. And you can also have systems with just M mode and U mode, which is then like some secure embedded system where you have some security environment and user code running below that. So there is actually no separate modes for virtualization. You just split up S and U mode into HS and VS, or HU and VU mode. One is the hypervisor side, which is the native side, and one is the virtualized side, which is running under the hypervisor and goes through to stage address translation. But this is the last time I'm going to mention hypervisor stuff because it's really complicated, but I assure you it's there and it works. So that's all I'm going to say about it. I already mentioned traps a bunch. Traps are basically the general name for synchronous exceptions like illegal instructions, asynchronous timer interrupts, and all the asynchronous interrupts that come from hardware, interrupts from like the various interrupt controllers and so on. And by default, whenever a trap occurs, it gets taken into M mode, and M mode can delegate traps to S mode, which is usually done to handle things like page faults and so on. And like you can see here, like MEDELEC and MIDELEC, those are all CSRs. So that's again things that CSRs are used for. The interrupt vector table decides, depending on which mode you're in, MTVEC or STVEC, decides where the trap actually jumps to. And then there is a bunch of CSRs that the hardware writes context into. For example, the instruction that faulted, the exact cause and other information, the program counter, and so on. So for example, for pages, page faults, it will tell you accessing which memory location faulted, of course, so that you can handle that. So again, keeping on the topic of traps, the way that you do various calls to the underlying higher privilege mode is through environment calls. It's an eCall instruction. It works the same on all privilege levels. So an eCall from U mode to S mode is a system call. An eCall from VS mode to HS mode, so from a virtualized kernel to a hypervisor kernel, is of course a hypercall, and an eCall from S mode to M mode is firmware call, and this is supervisor binary interface call, whatever you want to call it. It's all the same instructions, which I don't think that many architectures do. Not even ARM does that for some reason. They are just synchronous exceptions or synchronous traps, and there are special instructions for returning from them, which is, by the way, the same for the other traps, SRED and MRED. So the already mentioned the SPI, there is a standardized interface for how the supervisor, so the kernel, talks to the firmware, and that's through the supervisor binary interface, the SBI. And there is a certain small number of functionality that has to be provided, and then there's a bunch of extensions that can optionally be provided. For example, here, it's kind of hard to read, but this is basically using the debug console extension to write a single H to the debug console. And you can see the eCall at the end there. It's again implemented through environment calls. And there's a bunch of functionality that really depends on what system you're on, which can be implemented this way. And there's also, in the term SBI, you'll probably see an open SBI, which is the standard implementation or the main implementation for SBI, which of course is open, as the name implies. So in terms of firmware, since we're already moving towards firmware stuff, RISC-V uses device trees at the moment. Some people try to implement ACPI. Despite my discussions earlier, I have the firm stance that ACPI is evil and must be burned at all costs. So please don't. But technically, yeah. Also, it runs UEFI. So specifically, this system is running UEFI with device trees on top, which is possible despite what you might believe. It's already established, kind of. So this is nothing new. RISC-V is not doing anything special here. U-boot and other bootloaders support RISC-V on many systems, as do various kernels, obviously. So that's already the end of my talk. Now it's your turn. What will you do with RISC-V? Yeah, thank you for listening.
Thank you very much, Filmröllchen, for this amazing overview of RISC-V. Questions? Yes. How do we get there?
You mentioned all the extensions. How does this play with packaging for distributions like Debian, for example? What happens if there's an extension missing for the programs which came from the package manager? Or the other way, how do programs take advantage of existing extensions which may not be the absolute default minimal set?
Yeah, okay. I'm just putting up this slide because you can see the MAFDC. I didn't talk about A, but it's of course the atomics extension. So the thing is, for one, there are sets of extensions that are standardized. The main one you might have heard of is G, which is the general purpose computing extension, which is IMAFD, ZICSR, ZIFENS, ZFNAPOT, and ZFINVAL or something like that. There's a bunch of other ones. once you get deep into this standard extensions with the Z's, they have like very weird specific functionality. But basically, there is a set of them that are standardized, and this is also running RV64GC. So yeah, general purpose with compressed instructions as well. Didn't mention compressed instructions here for a reason, because they're garbage. But yeah, the other thing is that even though you might have like the G instruction set, there's this bunch of things missing that you need for general purpose stuff. So now they're moving towards specifying profiles, which are slightly different, but basically the same. But probably in the future, we're going to have these kinds of profiles that we're going to work by, which are also just collections of extensions that need to exist and a certain number of tests that need to pass, which is all going to be open, or is all open. And for another thing, there's actually in the ELF specification for RISC-V, they actually have already a few fields for this binary requires this extension. For example, you might require a binary which behaves in terms of memory like x86. Won't go into detail about memory models and stuff. I purposefully left it out, but basically some applications might need that for legacy reasons. So, and not because not every processor implements that, you can then say, okay, this binary can't run on this computer because there is a certain flag in the ELF header that tells you, I would need this extension, but I don't have it.
Okay.
Any other questions? Yes.
What's the most common extension you know?
You mean from the standard extensions?
Sure.
That are implemented? I mean, I have not yet seen any system that doesn't have the multiply extension. So I think the multiply extension would be the one. Like even these ones here are RISC-V 32 IMAFC, I think. So they even have compressed. So they have multiply atomics. Wait, okay, this one has multiply atomics, floating point, and compressed instructions. But I would definitely say that the multiply extension is the most common one.
Okay, thank you.
As a potential end user of such a system, I'm kind of worried about all of these different extensions and me looking at some weird table choosing which hardware to buy so I can run my software. Is there any intention to kind of group different kinds of extensions into like a feature level so that an end user can have an easier time to understand what the machine can do?
Well, basically, if you just buy general purpose machines like laptops or whatever, it's probably going to be the most recent standard profile, which is some variant of RV64GC. So there's, for like the end user stuff on that side, there's not going to be a lot of variation, of course, on purpose. The main thing with the extensibility is that if actually for application specific stuff, like when you're going from microcontrollers to very weird specific systems and various embedded stuff. And I think the platform, it's the same way that already package managers and distros already tell you, okay, this package has the wrong architecture for your system. It's going to be the exact same way, and there's going to be this lowest common denominator, which are these RISC-V profiles, which is the same way that, you might not have AVX, for example, on your laptop with x86. And so you can't run software that requires AVX extensions. I think it's going to be very similar.
Thank you. There's another question. Where was it? Oh, thanks.
Do you know how many microcode? Oh no. No, I don't know the name. So, how many microcode instructions exist?
You mean implementations, or?
Yes, as I understood, some of the instructions are based on several microcode instructions.
Well, no, there is. So microcode, as the name implies, belongs to the microarchitecture, so it's not visible from the ISA level, from RISC-V's point of view. That depends on your implementation. The way that like x86 is such a complicated instruction set is that you actually translate it into RISC instructions before it gets actually processed by your modern CPU. And this is kind of happening for RISC-V, but is only necessary at a much, much, much later stage at much higher optimization levels. Like I have not seen, I've read several design documents of open source processors, and they all don't do that. It's rather that you do the opposite, where you combine multiple instructions into one, and that's of course macro-op fusion, because then we are combining things together again. But that will always depend, microcode stuff will always depend on your implementation.
Any other questions? Okay, if that's not the case, I think that's the talk. And yeah, thanks to Filmröllchen again.